Welcome. Today we're going to be looking at FST quiz for 8.3 and 8.4 dealing with radicals. Starting with number 1 here, multiplying using the product rule. So first of all, since these are both cube roots, then we can go ahead and multiply their radicands together. So we get the cube root of 25x times 49x. And so we can multiply the 25 and the 49 together, that gives us 1,225, and multiply the x's together, that gives us x squared. Now of course we'd want to reduce this if at all possible. However, knowing where the factors for 1,225 come from, I can determine that there are no factors repeated 3 or more times. Also, the x squared is a lower degree than 3, so nothing can be reduced there. Simplifying a radical like this one, we are going to assume all our variables represent positive real numbers, so we're not going to have to worry about absolute values or anything here. I would go ahead and split this up as a fourth root of s squared over a fourth root of 81. Now the fourth root of 81 is 3, because 3 to the fourth power is 81. Fourth root of s squared would be the same as s to the 2/4 power, which would reduce down to the 1/2 power, which then I'd want to put back to be the square root of s over 3. So it is important here that we are assuming that the variable represents a positive real number, because then the square root of s is going to be real always. And moving on to number 3, simplifying a radical like square root of 150x squared. It's not perfect, so we need to figure out how to split this up into what we can square root and what we cannot. The largest perfect square factor that goes into 150 is 25. 25 times 6 gives us 150. So we split it up this way. We can square root the entire x squared, so we put that in the first radical. We square root the 25x squared, we get 5x. The 5 look a little bit 5-ier for you. And then the square root of 6 stays the same, and that's it. And again, we are assuming that the variables represent positive real numbers, so we don't have to worry about absolute values there. Same sort of simplification process for number 4. We do have this negative on the outside. It's going to kind of just go along for the ride. So I just keep track of that by putting that in front of our first radical. Otherwise, we're looking at splitting this up. The largest perfect square factor of 50 is 25. 25 times 2 is how we would split that up. We can't square root k to the 7th, but we can square root k to the 6th. So that leaves us a k in our leftovers. And we can square root the entire q to the 8th, so that would go there. The negative is going to be there. 5 is the square root of 25, k cubed, and q to the 4th, and then the square root of 2k just along there at the end. So that's what that one would look like. And then number 5, switching up to cube roots. Now remember, you can cube root a negative. You could also pull the negative out of the cube root either way. Ends up being the same thing. I would just think of it as a negative 27 that I'm cube rooting. I cannot cube root a to the 8th, but I can cube root a to the 6th. That leaves me an a squared left over. Likewise, I can't cube root b to the 5th, but I can cube root b cubed. That leaves me a b squared left over. Cube rooting the negative 27 gives negative 3, and then we get a squared and b, and the cube root of a squared b squared. So that's what that one turns out to be. Number 6, another cube root. Cube rooting y to the 20th and 216. Again, I can't cube root the entire y to the 20th. I can cube root the 216. That's just 6. I would have to split up the y to the 20th into what I can cube root and what I cannot. Really, we're looking for the largest multiple of 3 that's less than or equal to 20. That would be 18. Leaves me with a y squared left over. 18 divided by 3 is 6, so that's a y to the 6th power, cube root of y squared over 6. And so that's what number 6 looks like. Moving on to number 7, they want us to simplify, and in order to do that they suggest first writing with the radicals with the same index and then multiplying. So the issue is we have a square root of 3 and a cube root of 4. Now that would be a 3 to the 1/2 times a 4 to the 1/3. And the issue there is they have different denominators in those fractions, so I want those to be the same. The LCD for 2 and 3 would be 6. You might also think of this as the LCR, the least common radical or least common index. So in order to get the least common denominator to be 6, 1/2 is 3 over 6, 1/3 is 2 over 6, so we end up with the 6th root of 3 to the 3rd power times the 6th root of 4 to the 2nd power. 3 to the 3rd is 27, 4 to the 2nd is 16, and so we would multiply those together. We get the 6th root of 27 times 16, which becomes 432. And again, knowing where those factors for 432 come from the 27 and the 16, we don't have any factors that are repeated 6 or more times, so we cannot reduce that at all. Here we're just adding these radicals together, so 4 square roots of 11 plus 3 square roots of 11, those are like radicals. And kind of the long way of looking at that is you factor the square root of 11 out, you're left with 4 plus 3, and so you end up with 7 square roots of 11. Kind of the fast way of looking at that is almost treating it like it were 4x plus 3x, which of course would be 7x, except instead of x we've got square roots of 11, so 7 square roots of 11 there. Number 8, a little bit different, or sorry, number 9, a little different. We've got 9 square roots of 7 minus 2 square roots of 28. Now the square root of 28 will reduce, so we want to do that before trying anything else. So that 9 square roots of 7, we're just going to leave that alone for now. Square root of 28 reduces as a 4 and 7. We'd use the 4 and 7 because, of course, 4 is a perfect square. Square root of 4 would be 2. We already have a 2 out there, so we would multiply those together, those 2's. And then we see, well, we actually have 9 square roots of 7 minus 4 square roots of 7. And so just combining those 9 minus 4 gives us 5. So we have 5 square roots of 7. That's what we end up with for number 9. Number 10, similar problem. That 4th root of x to the 7th will simplify. So we can split that radical up as an x to the 4th. Sorry, 4th root of x to the 4th times the 4th root of x cubed minus the 4x times the 4th root of x cubed. 4th root of x to the 4th would just be an x. We still have the 4th root of x cubed minus 4x and the 4th root of x cubed. So we have a lot of things working together here, particularly how we've got 9x minus 4x there. And again, this is a 4th root, not an x to the 4th power, so make that look a little bit better. And they're both 4th roots of x cubed. So these are completely like terms. We can just do the 9x minus the 4x and get 5x times the 4th root of x cubed. And that is what we end up with for number 10. Moving on to number 11. Again, it looks like we could try to simplify the cube root of 64x and the cube root of 27x. And with this one in particular, the cube root of 64 is 4. And so we'd still have that cube root of x that we can't do anything with. Cube root of 27 likewise is 3, and we still have the cube root of x that we can't do anything with. So we end up with 8 cube roots of x plus 6 cube roots of x. So adding those cube roots of x together, 8 plus 6 gives us 14. So 14 cube roots of x is what we end up with for number 11. Now number 12, looking at that, we get that square root of 6/7, which will not reduce at all. And then we've got the square root of 216 over 252, which certainly looks like it will reduce. And so leaving that square root of 6/7 alone, but splitting up the 216 over the 252, what ends up happening is we can factor out some different pieces here. So really taking a 36 out of the numerator, which leaves us with a 6. And we actually take a 36 out of the denominator as well. So really looking at this, the square root of 36 over the square root of 36, there's a few different ways you can go about simplifying that, but this is really equal to 1. And so we really could have just reduced the 216 over 252. That leaves us with square root of 6/7 minus the square root of 6/7. Those match up exactly. So we end up with a total of 0 for number 12. Now looking at number 13, we've got a square root of 3x minus a square root of x over a square root of 3. There's a couple different ways you could handle that. I think what I would probably look at doing would be to first rationalize the denominator for the square root of x over the square root of 3. So just leaving that square root of 3x alone, we've got the square root of x over the square root of 3. To rationalize, multiply by the square root of 3 over the square root of 3. So we get the square root of 3x minus the square root of 3x over 3. Now if I'm going to actually combine these, I need a common denominator. The LCD would be 3. The square root of 3x over 3 already has that for its denominator. The square root of 3x, really over 1, needs that for its denominator if we're going to combine them. So multiply top and bottom by 3. And so we end up with 3 square roots of 3x over 3 minus the square root of 3x over 3. So again, emphasizing that there's one of these. So take 1 square root of 3x away from 3 square roots of 3x, and we end up with 2 square roots of 3x over 3 for number 13. Well, thanks for watching, and hopefully this was helpful. If you have any questions, be sure to let me know.